Okay, so I'm going to try to go through this kind of the way that I do it. It is just in general kind of confusing, but I'll just kind of do my method that I've tried to piece together. So first, I'm comfortable with IR spectrums. I'm going to look at the spectrum and try to figure out what I can tell from it. So right away, I'm looking at this right here. This is an intense peak, and it's right around 1680, so that's going to be a double bond, but because of its intensity, I'm really thinking that it's going to be an oxygen. So this is what I'm thinking so far. So IR, I think right now we're going to have this. Through my own research, if you look at this area right here and this area, I just did my own research about IR spectrums just to try to piece everything together. So these are where our SP hybridizations are going to come into play. And with these peaks right here, it's honestly telling us that we're probably going to have SP, SP2, and SP3 hybridization within this molecule. And right here we have what are referred to as aromatic overtones, which could be an indication of a ring, particularly benzene. I know we didn't discuss this in class, but whenever I started figuring out that rings would be in there, I found that this is a decent enough method to be able to identify that rings could be a part of your molecule. But so yeah, there's that for now. So I'm going to go down to the mass spectrum now, and I'm going to get as much information out of this as I can. So first, let's consider the H+. We're going to look at the H+, which is our next to last, basically, spot. So it's going to be this bar right here. If we look at all of this, this tells us we do not have a bromine and we do not have a chlorine. So we're going to assume there's no halogen, because if it was bromine, it would be little tall, roughly same length here for these four right here. And if it was chlorine, it would look something to the effect of like this. You have little, tall, little, really tall. We don't have any of that happening, so we can assume that there are no halogens. So I'm just going to go ahead and start by saying that. So there's no halogens. But at our H+, this is this position right here. We see that we have 148. And with that, we're going to go ahead and do, up here we decided, we think that there's this oxygen right here. We're going to do that 148 and subtract 16 to account for that oxygen, because we really think that there's an oxygen there. So that's going to leave us with 132. We're going to use the rule of 13 for carbons, because we're going to identify how many carbons we have. So let's divide this by 13, and that gives us 10. So it seems like we're going to have 10 carbons, right? So that's what we can determine from this right here, right now. Next, I'm going to come down. I'm going to look at the HNMR. And what I'm going to do for this is, we have 5 signals, right? I'm going to label them all different letters, because we're going to need to keep them separated, because there's a lot of information associated with each one. So this is going to be A. This guy's going to be B, C, D, E, and F. And if we look at the numbers, we have 2 hydrogen, 1, 2. We have 2 hydrogens, and then we have 2 and 3. And if we add up all of these hydrogens, we get, because here we're not given the, I forget what he called it, where there would be numbers that we would divide by the smallest number. I forgot what that's called right now, but we don't have those numbers. So we're going to assume that it's telling us already how many hydrogens we're going to have in our molecule. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's roll with this and see what we get for an HDI. So according to this, we have 12 hydrogens. So let's see if that's the case. Let's do an HDI to see what it gets us. Because up here we assumed a ring and a double bond. This is 5 HDI. So let's go down here. If we have 12 carbons, so right now we think we've got C10H12O. Question mark, question mark. Let's do an HDI. We have 2 times 10 plus 2 minus 0 nitrogens. We have no nitrogens. Minus 12 hydrogens minus 0 halogens. Let's divide all of that by 2. Lo and behold, we get 22 minus 12 over 2. That's going to give us 5. So, based on this, our HDI here matching up with this HDI up here, I say we're off to a pretty good start. I think that everything's correct. Everything's matching up, which the way I see it is like the odds of everything matching up and falling into line based on what we've viewed so far. I mean, come on, slim to none. Here's where it gets fun. We're going to hold a lot of information in our little brains right now. So let's analyze all 6 of these. So we got A. There are 2 hydrogens, right? There are 2 peaks. This is just from that. There are 2 peaks. 2 minus 1. This is that N minus 1 formula. We're going to have 1 neighbor. I'm just going to put N for neighbor. It's going to have 1 neighbor. That means between everything that's attached to this carbon, only one thing attached to it has 1 hydrogen. So we know that. Let's look at our ppm. We got roughly 8 ppm. All right. So let's see. Let's move to B. B has 1 hydrogen. It has 1, 2, 3 peaks. 3 minus 1, 2 neighbors. Right? We got roughly a 7.5 ppm. Cool beans. Love it. Let's move to C. C looks just like B. Well, similar. It's got 2 hydrogens. It's also a triplet. Minus 1 and minus 1. We're going to have 2 neighbors on this one as well. Again, roughly 7.5 ppm. Let's move on to D. All these bitches look the same. Oh, all these peaks look the same. We got 2H. There's 2 hydrogens at this specific position. We got 3 peaks. 1, 2, 3. 3 minus 1. We got 2 neighbors again. Roughly 2. That's not a 2. 2.9 to 3 ppm. Whatever. Same diff. Okay. E. 2 hydrogens at this position again. We got 1, 2, 3, 4, 5, 6. 6 minus 1. We got 5 neighbors. ppm. Don't know why I'm stroking out. 1.8 roughly. Alright, let's move to the next one. Last one. Last one, best one. 1, 2, 3. We got 3 hydrogens. Sorry, that is from that number. I made that very confusing. It's a triplet minus 1. We got 2 neighbors. ppm, roughly 1 ppm. Now we've identified some stuff. Okay, so now this is the part that to me is the hardest to explain. Personally. Yeah, I'll do my best to explain this part, like constructing it. But yeah, it's kind of difficult. So let's start with one thing. As of right now, knowing we have these 2 things going on, knowing that we think we've got these 2, it matches up with the HDI, it matches with everything. Let's see how many carbons and hydrogens we would have used up by now. So, taking these into account, we have 1, 2, 3, 4, 5, 6, 7 carbons. So, I'm going to say we have 3 carbons remaining, and we have 1, 2, 3, 4, 5. There is not going to be a hydrogen here, because this would just be an independent ring if there was a hydrogen there. That's not going to be the case. What's going to occur is something's going to come off of this. So, we've used 5 hydrogens, so we still have 7 hydrogens left. I'm just going to kind of file that back for later so I don't get too crazy and make a huge molecule when I don't need to. So, let's start looking at some stuff. Let's look at... Alright, so what I want to do next is I want to just go ahead and... We're going to start working with these ppms. let's go ahead and identify what we know these to be. We know that this carbonyl is going to be roughly 1 ppm, right? We know that this ring is going to be roughly 7 ppm. That already kind of gives us a good start, because we've got some higher numbers, like with this, with A, B, and C, honestly. We got some high numbers. These are 3 separate signals. A is a signal, B is a signal, C is a signal. So let's kind of look at this ring real quick. I'll bring it down here. Make it a little bit bigger. Nope, that was not making it bigger. Bear with me, I'm dumb. Okay, so let's look at this. Let's look at A, B, and C, because these are obviously going to be closely associated with this ring. I'm going to assign some positions. Everything here is a hydrogen. These little purple lines, each one is a hydrogen. So, what this is saying is, essentially, let's look at B. We can look at either one. Let's just start with A. So we're obviously going to have stuff coming off of this side. So this has the highest ppm, and if we go by the fact that we're going to be alpha and beta and whatever to all these other positions, so we're going to start with that 7 ppm from the ring. We're going to add to it. This has to be the closest to all of those other groups coming off of the ring, if that makes sense. So I'm going to go ahead and say A positions are here, because we're going to be adding to these ppms with however much. Pretty confident that that's A. From there, and it works out, there would be 2 A positions, because they would not be distinguishable from one another, right? They would share a signal. So there are 2 hydrogens that would share a signal, and they each only have 1 neighbor, because there are no hydrogens here. Okay, let's move on. Everything's pointing to A being there. Let's look at B. So B has 1 hydrogen. Now that's different, because it means that there is nothing sharing a signal. There is 1 hydrogen on this signal. There are not multiples. Okay, well, if we put B here, what happens then? Well, you could also have a B here. There's symmetry there. So what we're going to have to do, put that B here. Does it work? It has 2 neighbors? I don't know why I drew an A. There's a neighbor here. There's a neighbor there. That feels really good. That feels great, actually. Next, last up, we have C. Let's try it out. If we put C here, there are 2 of them, C1 and C2. There are 2 of them. There's symmetry. There are 2 hydrogens on this 1 signal. Let's see how many neighbors they have. 1, 2. Okay? And then this C has 1, 2 neighbors. I feel really good about this. This ring is where it's supposed to be. It exists in space, and it has been rationalized by basically all of our graphs. We got the 2 neighbors, we got the 2. I'm going to move this bad boy down here. Alright, let's start looking at the rest of them. Okay, now I want to look at all of these. So let's try to construct something from all of this, because we know, based on, let me bring some more info down. Based on what I decided here, we've only really got carbons to work with. So D, E, and F are all going to be a carbon molecule. So let's look at our neighbors and everything. The big one that stands out to me is this 5 neighbors. We've got 5 neighbors here. And it has 2 hydrogens at that position. So let's just go ahead and draw something like this. How are we going to get 5 neighbors? I've got the 2 hydrogens here, and I'll draw the neighbors in different colors. Hydrogen, hydrogen, hydrogen. This would also have to have 2 hydrogens. Well, what's going to have 2 hydrogens? We're going to have another carbon, like so, and this is going to have 2 hydrogens. So now we have this one worked out, as if this is E, right here. It has 5 neighbors, and it has 2 hydrogens on that position. So now we really have all of our pieces. Let's see. Let's make sure everything adds up. We've got this here. Let's look at F. F has a ppm of 1. What does that coincide with? A methyl group. A methyl group has 3 hydrogens. It's all coming together. Okay, so we've got this. Let's look at D, just to make sure we're on the right track. We've got D. D has 2 hydrogens. We distinguished that this right here would have 2 hydrogens. And 2 neighbors. Well, this had 2 hydrogens off of it, so it would have 2 neighbors. Perfect. This all feels like it's going really well. Okay, let's count how many carbons we've used now. And this isn't necessarily a carbon right there. That's just where it will be connecting. So I'm going to use a different color we haven't used yet to count all these carbons because it's everywhere. So we've got 1, starting on the benzene, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We have all of our pieces, methinks. Okay, so now let's start assembling. Okay, so let's take a look at this and try to assemble stuff. So we're going to start recalling some ppms. So let's recall A's ppm. So A had a ppm of 8, 7 from the ring, right? So where are we going to get that last ppm? Based on everything we have here, where could we get another ppm? We could get 1 full ppm if this A position is very closely associated with this. So let's see what that would look like. Because this carbonyl is 1 ppm. So let's see. Let's attach a carbonyl right here. Okay, now let's move along. Let's see how this would attach. And there's really only, if we think about this, and we're considering this a methyl group, can a methyl group attach right here onto this molecule? Can a methyl group go here? It can't. That would overload the carbon. The limit does not exist. You know what I mean? You can't put a methyl group there. So what we're going to do is we're going to take D and connect it right there. So that's going to give us something like that, I believe. I feel like I have 1 too many carbons. Let me see. I do. Like that. Let's count our carbons. Just to see if we got all the pieces in there. Because remember, let's recall our formula that we came up with was C10H12O. Let's count some carbs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. I love it. We got our 10 carbons. Let's count some hydrogens. We need 12. We have 1, 2, 3, 4, 5. No hydrogen there. No hydrogen there. 6, 7, 8, 9, 10, 11, 12. Okay. I love it. It's beautiful. I love when things just work out. I mean, we applied copious amounts of effort. I'm not just going to say that they worked out. But we have all 10 of our hydrogens. We have this oxygen. Perfect. It looks great. I think it looks great. From here, what you can do is we assigned everything a position. So let me rewrite those. Now this would take a bunch of time. But what you can do from here is you can go in and calculate the ppm of each position based on what it's next to. So for instance, you have, it's a methyl group. It has a ppm of 1. Up here, it had a ppm of 1. That checks out. So you could go through and do that for all of them. For example, let's see, D. I think D is the one I struggled with the most. So let's do E. E had a ppm of 1.8. We had a ppm of 1.8. Well, this is a methine group. So a methine has a ppm of 1.2. Okay. So now we've got to figure out where did the other 0.6 come from.